Raphael, that's me, and Shania. And to introduce the problem that we've been working on, we'd like you to think about the following idea. So imagine that you're a Duke researcher who knows that you need around 128 gigabytes of RAM and 32 CPU cores to process whatever workload you have. Now, being a Duke researcher, you have the privilege of having access to the Duke compute cluster's resources, but perhaps the Duke compute cluster doesn't have what you're looking for immediately available at all times, and you might be willing to try your luck looking for these resources in a commercial database. Now, I know that if I were a research having to parse through all the best deals in commercial databases and familiarizing myself with cloud market mechanisms, it's probably not the best use of my time. And I would be very grateful if some other group who had some time on their hands were able to provide me with the resource that would make that whole process more intuitive. And that's where our group comes in. So cloud arbitrage essentially means that we're looking to see how we can help Duke researchers find the best deal for computing resources made available by cloud providers. And there are three main ways in which cloud providers make their resources available. It's either through on-demand instances, which means that you pay for the resources that you need on the go. There are reserved instances, which are more discounted as compared to on-demand services, but they require a longer-term commitment, generally from 1 to 3 years. And then there are spot instances, which are unused cloud capacity sold at heavily discounted rates. And for our project, we'll be looking at Amazon Web Services and Microsoft Azure commercial databases. And we're mostly interested in spot instances. And the reason for this is because being leftover computing capacity, they can have cheaper prices as compared to on-demand instances that can reach up to 90%. And an example of this, taking the idea that we presented in the previous scenario of 32 cores and 128 gigs of RAM, can be seen in an image below here. So it would be a $900 difference in this case. But spot instances are also really challenging because they're based on a bidding mechanism. And so you only get access to the spot instance if you currently have the highest bid for it. So there's no service level agreement that will assure your continued use of this resource for as long as you might perhaps need it for. And this can lead it to have up to 30 to 40% risk of being terminated for the user. And so we have this challenge. Spot instances can be a really great deal, but it's hard to know when to invest on them. And so Shania, why don't you explain a bit about the solution that we've been coming up with to this issue?
Sure, thanks, Raphael. So to kind of help researchers find the cheapest deals in computing resources made available by cloud providers and also looking at how we could best use the DCC, our team has built a dashboard that predicts market trends and helps them determine whether it makes sense for them to run on a particular spot market instance. And on our dashboard, we've created models that are based on both historic and recent pricing trends. So researchers can have a kind of an overview of the different computing resources that they have access to. And so our project can be divided into three main parts. The first part being data collection and analysis. During the first stage of our process, we did an in-depth market analysis on the different cloud providers. And we also did a bit of a deep dive into the DCC, looking at the different types of memory that were there and also the availability. And then we went into doing future predictions for the DCC data and the cloud providers. So we did pricing predictions for the cloud providers and then availability predictions in the DCC. And lastly, we made a big dashboard. Sorry. So our dashboard works as a final one-stop shop for our researchers, and it has lots of interactive features that helps researchers kind of decide what their CPU usage is and what their desired memory is, and then type it on our dashboard and they can kind of get an overview of the resources available. Najib, do you want to talk a bit more about our dashboard tools?
So these are the different dashboard tools we'll be using on our dashboard. We use the coding language of Python to code everything. And we also use Jupyter as the main platform when we did all of our coding. We use HoloViews and Plotly to create our visualizations and use the Jupyter package of Voila to visualize it in a dashboard. Finally, we use GitLab to collaborate and share our work. And I'll pass it on to Betania to speak more about our methods.
So I'm going to start off by talking about the Duke Compute Cluster. The DCC runs on Slurm, which is how work orders are processed and scheduling occurs. We use the command S account in the terminal to display information over the past 30 days. And on the 30th day, S report kicks in. This means the DCC is working with a 30-day time frame to get all job information. We also use the command S info to view partition and node information on the terminal as well. The DCC is focusing on the scavenger and scavenger GPU partitions. And with the commands I talked about in the previous slide, we've been able to filter data based on specific time parameters to gather our final information. And with our preliminary information, Duke IT has been able to change data allocation incentives for researchers. So this means they've been able to offer researchers more RAM to move off heavily used partitions such as common and onto partitions that encounter less traffic. So this is helpful for everybody. So far, we've been able to automate data collection using Scron. So every 15 minutes, new data is uploaded into the DCC. We have 3 interactive models, one for historical resource availability, another for 24-hour usage, and a third for current job information. We also have a table that takes in user input to find the max RAM based on the CPU amount the user desires, which we'll show later in the slides. And this is an example of one of our interactive graphs where the user can decide on the date, the partition they'd like, and the resource they'd like to view as well. Now, Jalen, can you take us to our next?
Shania and I have been working on Amazon Web Services. The first thing that we had to do was scrape the data. We did this on the Amazon Web Service command line interface, extracting the past 90 days of AWS Spot instance data. On the left is how it is viewed on the AWS dashboard. As you can see, there are 4 different filters, including availability zones, instance type, platform, and data range. We extracted it and then uploaded it onto Jupyter. On the right is how it looks in JSON format. And we did this so that we can ensure that we have a world view of AWS data and make it easy to find the cheapest spot price. Shania, could you share about how we initially visualized this?
Sure. So to kind of understand a few basic trends, we decided to make a few static visualizations. And we made 2 main visualizations. One was looking at pricing by availability zone, and the other was looking at historic pricing graphs for one particular instance type in one region. So as you can see on this slide, we have 2 graphs which have very basic trends showing which area probably has the cheapest spot price, and also how the spot price changes for one particular instance type in one region. And then our next stage was kind of to level up these visualizations and add an element of interactivity. So we kind of created this, we coded this, and we kind of added a place for researchers to type in like the desired RAM and number of CPUs, and an output would show up, which would be a visualization that represents the pricing trends for that instance type that meets the user's needs. And we'll be showing more demos of this towards the end of the presentation. Najeeb, do you want to talk a bit more about Microsoft Azure?
Yeah, so me and Angela are using Microsoft Azure. Similar to Amazon Web Services and Duke's Compute Cluster, it is a cloud computing web service. We use the Azure Retail Prices API, also known as REST API, which has all of Microsoft Azure's data compiled. From that API, we then create a code that scrapes all of the data collected in the past into a single CSV file. Using a cron script, we scrape that data every day at midnight, so the data is always up to date. From that scraped data, we filtered and manipulated it and merged it with the spot eviction data we collected using jQuery on Microsoft Azure to create an interactive visualization where we can better see the changes in prices. We incorporated those visualizations into the dashboard where Duke researchers can find specifically what they are looking for. And I will now pass it on to Angela to speak more about our dashboard.
The Azure dashboard now takes in 3 user inputs: the desired number of CPU cores, memory, and the desired range of eviction rates. The website then outputs 4 data visualizations, first presenting the 5 cheapest within the US, and then the 10 cheapest SKUs globally, and then a historical pricing graph, which we'll talk more in depth in a later slide. And lastly, a price distribution to help researchers understand where any particular price stands across all SKU pricings. And now Jalen will talk about analysis on both Azure and AWS.
This graph displays spot instances from AWS and Azure that align with the user's desired RAM and core. It shows the prices of these spot instances per month. This graph is with 128 gigabytes and 32 cores. From this graph, we can see that AWS spot prices are significantly a lot higher than that of Azure. And this insight can help researchers determine whether they would want to run on a spot instance from AWS or Azure. Because personally, I would want to save money and run on an Azure spot instance. But Tanya, could you share about our future predictions?
Yes, so currently our main modeling techniques are ARIMA, Holt Winters, and SARIMA. ARIMA looks back at time series to determine a baseline trend and then makes predictions based on what the variance could look like. Holt Winters uses exponential smoothing and seasonality to output a predictive trend. And our third predictive model, SARIMA, combines these 2 aspects of ARIMA and Holt Winters to output a predictive model. Shania, could you start us off by talking about AWS?
Sure. So for the AWS database, our first step was to kind of do some ARIMA modeling. And so as you can see here, we asked researchers to input their desired instance type and the availability zone they're interested in looking at, and then the product they're going to run this instance type on. And so once they hit submit, you would be able to see a prediction of the price of that particular spot instance and then the confidence interval. And we conducted a similar analysis using a different modeling technique called Holt-Winters. And as you can see here, the test and prediction have quite a significant divergence and quite a significant difference. And so therefore, when evaluating which model to use for our data, we decided to go with the ARIMA model because it fits better, especially in the shorter term, has a fairly low confidence interval. However, the Holt-Winters model deviates significantly. And given that, we decided not to go with SARIMA as a modeling technique for the AWS data set, given that it's not at all seasonal, and therefore maybe these seasonal modeling techniques wouldn't be a good fit. Raphael, do you want to discuss a bit more about the modeling techniques you use for the DCC database?
Yeah, for sure. So similar to AWS, first we looked at ARIMA for DCC. And if we look at the first short-term image here, we can see that it's quite accurate in the red highlighted rectangle. And this is the first 6 hours of prediction, which is what our groups mainly focus on when presenting the dashboard. But when we look at the longer term prediction, we see that it quickly flattens out. And so it doesn't seem to be very accurate. And this is because of its autoregressive nature. So when it runs out of terms, it doesn't really have anything else to output. And because of this, we looked at the Holt-Winters model, which was more based on seasonality, and we hoped that it would solve this long-term issue. And it did a little bit because it's able to predict some of the peaks and valleys in the data as we see in the longer term prediction, and it's still relatively accurate in the short term prediction. But since we knew that it was successful in the long term in terms of its ability to predict the peaks, we wanted to combine this with the ARIMA model by using SARIMA. And so we added the seasonality component to see if that would fix the ARIMA issue in the long term. And unfortunately, it wasn't as relevant a result as we expected it to be. And because of this, we're probably just going to use ARIMA in the dashboard, similar to what is being done with AWS. And so, Angela, why don't you explain the situation with Azure in terms of predictions?
So for Azure, there is no future pricing predictions, and that's because Azure SKU pricing is not volatile like AWS or DCC data. And new prices are usually released at the start of a month, and some pricings have stayed valid since more than a year ago. Therefore, our predictions on future pricings for Azure SKUs is simply that the pricing will not change. And here we'll take a look at what our dashboard looks like right now. So here's our dashboard workflow. Then DCC, Azure, and AWS will scrape their data separately from the websites, and the data frames are then cleaned and filtered by our website's user input, which are usually the number of CPU cores and RAM needed. And with the processed data, DCC and AWS team perform their future pricing predictions, and all the data and predictions are then presented, their graphs and tables, and shown interactive on our Voila dashboard. And now Najib will talk about the dashboard mockup.
So here's our first mockup dashboard design. Originally, we planned on having 2 separate dashboards. On the left is the first version of our first one, where we brainstorm the key concepts and features we would like for it to have. Those being Duke researchers entering the amount of gigabytes and vCPUs they like, then a table displaying the top 10 cheapest SKUs and a graph to go along with it. Although our current dashboard does not look like this, the initial concepts we had in mind have been implemented into our current dashboard. The second dashboard design on the right has the prediction features we wanted to have. This tool would tell researchers how busy the cloud was. We incorporated all these features from the first and second dashboard into a single dashboard, which Angela will demo.
So we now have 4 tabs on our dashboard. This is our homepage, which shows all 3 cloud providers that we have looked into. And then there's an individual page for AWS and Azure. And you can put in CPU cores and desired RAM, and it outputs all the visualizations that we talked in previous slides. Yeah, and then the third tab is for DCC, which shows you basically the availabilities that it collects with based on partition. And then here's a 24-hour graph. Yeah, so you can select the date and then memory or the CPU. And lastly, we have the historical job data. And here's the FAQ tab for some documentation for the researchers. And now Jalen will give a summary.
So to conclude everything, researchers can save money on spot instances, but there is risk in being terminated. Our team determined the cheapest and the best spot price for researchers' need by analyzing spot instance data from the Duke Compute Cluster, AWS, and Azure. With that data, we made an interactive dashboard that does two main things. The first, it models spot prices against time based on users' desired RAM and core. And the second, it makes predictions about future spot pricing for AWS and about resource availability for the Duke Compute cluster. And this is all so that researchers can be more efficient in their work. And the Cloud Arbitrage team has made incredible work during the 10 weeks, but this work would not have been possible without the help of our sponsor, Dr. Charlie Neifel, and the Code Plus team, Isabel, Jen, Echo, and Elise, and of course, our leads, Mark McCahill and Drew Stinnett. And that is the Cloud Arbitrage team. Can we answer any questions?